Overview of process control narratives and instrument protective function narratives. Due to the increasing complexity of control schemes required for optimum plant operation, it is often difficult to understand, unambiguously, the control intent or function of these schemes from their representation on process flow schemes, PFS, and process engineering flow schemes, PFS. Therefore, plain language descriptions, or narratives, are required to clarify the information on the PFS PHEFs so that they together form a clear statement of the design intent and operation of the control and protective function in question. In addition, the description of a sequence or batch operation cannot be deduced from the PFs at all, and thus a written narrative is needed to explain how a sequence or batch functions. Likewise, an IPF narrative is required for all IPFs. As part of the process control narratives and the IPF narratives, all control loops and instrumented protective functions of the plant are described in general terms. The process control narratives and the IPF narratives are to be written on a unit-by-unit basis. The process control and IPF narratives are separate documents. The IPF narrative forms Section 1 of the IPF requirement specification document for each process unit, as further explained later in this document. Detailed narratives shall be made for all complex control logic loops and for all IPFs. A control loop is defined as complex when the functionality and rationale cannot be unambiguously determined from the PFS or PEFs. Typically, this will be anything other than a simple master-slave cascade loop or a simple override control via one signal selector and includes any control that incorporates calculations. Both the process control narratives and the IPF narratives are living documents, where several sections are prepared and completed progressively as the project is developed during the definition phase, implementation phase, and subsequent startup and operation of the plant. The narratives shall form part of the relevant process documentation, design dossiers of the front-end engineering design feed. During the project definition phase, the narratives describe the detailed functional requirement specifications for all the controls and IPFs. During the implementation phase, the contractor will complete the narratives to the maximum available information and include them in the design book as part of the relevant process design dossiers. Control and IPF schemes within vendor package units shall be covered in the relevant unit process control and IPF narratives. Where control schemes cross unit/plant boundaries, control narratives shall be produced to describe the interaction and integration aspects of the control schemes. In addition to the above-mentioned narratives, Section 6 details further specific documentation that is required for controls that are integrated across multiple vendor subsystems. General aspects of the process control and IPF narratives. There shall be only one process control narrative and one IPF narrative document per process unit. These shall describe all the automation and instrumented protective requirements, including the functioning of various subsystems and their man-machine interface. The narrative documents shall be divided into sections such that they can be used in whole or in part by others, e.g. operating manual, DCS vendors, IPS vendors. Specific requirements are prescribed in the relevant chapters of this document. Both the process control and IPF narratives shall be developed and expanded progressively during the different stages of the project design as more detailed information becomes available. The process control narrative shall be produced and issued in line with the PEFs, and the IPF narratives shall be issued prior to the HAZOP and IPF reviews. Where responsibility for sections of the narrative is split between the definition phase and the implementation phase, the document shall be drafted in the definition phase, including functional requirements, and finalized in the implementation phase. During the definition phase, the feed contractor shall complete the narratives such that all functional requirements are specified. As such, the sections on background process information, control/IPF description, loop objectives, and functional descriptions shall be clearly defined. The functional requirements for multi-vendor subsystems, where available, shall also be included at this stage. The sections on operational and implementation aspects shall be completed as indicated. Where relevant, The feed contractor shall also set up the sequence function chart, SFC, and logic definitions, from which the actual sequence, batch, or logic programming can be coded by the control system vendor. During the implementation phase, the implementation contractor shall finalize the narratives by including all remaining operational and implementation aspects, e.g., constants in calculations, etc., in a manner that is consistent with the instrument engineering database in use on the project, ION tools. If the realized functionality differs from the initial functionality, this shall be detailed, including reasoning in the history section. Information from package units, as available, shall form an integral part of the relevant unit narrative. The system integrator, normally the developer of the unit process control narrative, shall develop the functionality overview narrative. The overview narrative development shall not be delegated to a subsystem vendor. The process control and IPF narratives are intended for use by contractors, process engineers, instrument engineers, maintenance engineers, and operators. The final as-built unit narratives will be part of the process dossiers of the design book. Parts of the narratives can be used for the operating manual. The process control and IPF narratives are the vehicle for the engineering contractor to communicate the detailed control and IPF requirements to the DCS/IPS vendor. The process control and the IPF narratives shall be used by the DCS and IPS system vendors as a functional specification, as well as for the detailed FAT of the DCS and IPS, and the integration tests with other vendor subsystems. The narrative documents shall give sufficient detail to start configurations, and shall be updated as detailed engineering, vendor data, implementation, and commissioning information becomes available. These documents shall also provide sufficient detail for detailed FAT testing. The IPF and alarm narratives will in a later phase be superseded by the IPF requirement sheets or even be replaced by the documentation in the RRM-CIF software. However, certain parts of the IPF narratives, like the sequence diagram and descriptions, cannot be replaced by the IPF requirement sheets and/or software, and need to be maintained as it is important for an understanding of the sequences. Moreover, in projects sites where a SIL IPF classification will not be done in the foreseeable future, the IPF narratives need to be maintained as described in this report. Therefore, at the start of documenting IPF alarm/sequences in a project or on a site, a decision needs to be made if the IPF narratives will be superseded or replaced by the IPF classification documentation. This will be an important scope item. Since the process control narratives and IPF narratives are living documents, they shall be made available in the definition phase and in implementation phase, respectively, in electronic format in line with the relevant project procedures. The control, sequence, and IPF narratives shall document the reasons behind each and every setting and calculation constant, and provide a cross-reference to the source of the data. This could be, for example, vendor equipment curves, e.g. burners, compressors, etc., vendor manuals, and flowsheet output. In addition, the values of control and IPF calculation constants shall be included in the narratives, along with how they are derived. However, the values of control or IPF settings like alarm or trip settings, timer settings, controller set points, ramp rates, output limits, etc., shall reside in the complex InTools database. From InTools, separate lists for timer lists, alarm and trip settings lists, or DCS parameter list can be produced as required. The control and IPF narratives and all associated documents and drawings shall be updated to as-built status by the contractor and thereafter maintained by the site. Process control narrative, content and structure. The process control narrative shall contain the following sections: process background information, control description, a walkthrough of the process briefly describing all controls on the unit, detailed control narratives, a detailed description of complex controls suitable for DCS vendor implementation, logic sequence batch control descriptions, control overview diagrams and complex control loop diagrams, diagrams for logic, sequence, and batch controls, SFC, timing chart, etc. Functionality overview, diagrams for complex interconnected subsystems, advanced process control, strategies for advanced control, usually multivariable model predictive control, e.g. SMOC, Non-control applications. Calculations implemented in the ODS. The overall structure of the process control narrative is detailed in the relevant appendices, with examples provided for guidance. Background process information. The background information gives a description of the process function of the plant, its subunits, and connected process equipment, e.g., separators, pumps, vessels, compressors, etc. The background information shall include as a minimum process objective of the unit, place in the overall site configuration, process interface with other units, brief description of the process, different modes of operation, where applicable, information on startup and shutdown, where applicable, of the unit. Control description. This section shall provide the functional description and the design intent of all the control loops, logic, sequence, or batch systems, and details of special instruments employed, showing how they fit into the overall control strategy. The effects of changes in the operating variables on the process and the requirements of the control system shall be described. For this section, the parts of the design book relating to control of operation may be used. The alternate operations, if any, provided for in the design are mentioned. Tag numbers shall be used in the control description, however, without any unit prefix unless the tag is from a different unit, i.e. in Unit 1600, 160 TITS 001 should be referred to as TITS 001, but 170 FFI 010 remains as is. Tag suffixes are only to be used where necessary for clarity. Detailed control narratives for complex loops. Detailed control narratives shall be written for all complex loops, i.e. any control, interlock functionality, and logic functions which cannot be clearly understood from the PEFs and PFS and which requires additional explanation. A complex loop is everything other than a simple master-slave cascade loop or override control via one signal selector. Detailed narratives shall also be provided for simple, master-slave or other loops with a complex process background, loops with special implementation requirements, all calculations, whether they are used in a control loop or not, all sequence control and logic operations, integrated controls that are implemented across multiple vendor subsystems. The detailed control narratives shall include all the relevant information to enable a full understanding of the control, implementation, and operational aspects of a particular control loop scheme. For basic, non-SMOC control loop schemes, the detailed narratives shall be completed prior to plant startup. For SMOC control schemes, the detailed narrative can only be completed after plant startup, since modeling and tuning has to be tested on an operational plant. Where control schemes cross unit or plant boundaries, a copy of the overview control scheme will only be provided in the most pertinent unit process control narrative, and cross-references to it shall be made in the other unit plant narratives. Tags described in the detailed control narrative section of the process control narratives shall be provided with service descriptions. The description shall include the following as a minimum: objective, functional description, operational and implementation aspects, history, timing. These are described in the following sections. Objective. This section shall describe the individual and overall process reasons and control objectives for the particular scheme, explaining what is being controlled and why, giving the reasons. For multivariable model predictive controllers, the objectives, e.g., increased throughput, improved quality, etc., should be prioritized, and a cost-benefit analysis of the control scheme should be given. This analysis cannot be undertaken until actual plant operating data is available, and therefore should be detailed in a separate section, as shown in the example narrative. Functional description. This section shall describe the control loop scheme, explaining how it works. Tag numbers shall be included along with service descriptors, and references made to the relevant PEFs drawings. Where multiple vendor subsystems are involved, it also describes how and where this is implemented. Operational and implementation aspects. This section shall comprise the implementation details and the operational aspects of the scheme. It shall be completed in the definition phase to the extent of available data. The implementation contractor shall complete final implementation details as more information becomes available. This section of the process control narrative shall also include the following: operational modes, startup, including initial plant startup, for instance with fuel gas, oil, or off-spec product, and startup after operation. Normal steady state, crippled mode operation, shutdown, abnormal conditions, calculations to be in tag number order, initializations, interfaces, operator interfaces to the controls, special considerations, a full derivation of all individual calculation constants, along with a cross-reference to the source document of the data for each and every value used. This could be an instrument datasheet, a control valve vendor datasheet, a set of compressor performance curves, a set of burner curves, a process flow sheet printout, distillation tray design sheet, etc. The document shall be referenced by number, title, and revision. Any special implementation details, including reference to the associated software loop diagrams. Operational limits of equipment, turndown, or of instruments, e.g. low accuracy if the product is off-spec, low cutoff point of vortex flow meter. For process control-related timers, the reason for the timer, whether it should be visible to and adjustable by the operator, and the rationale behind the setting. The actual timer setting shall reside in a separate setting list. History. The history section shall contain the details of the changes made to the control loop scheme during its lifetime to prevent modifications to the loop scheme that have already occurred at a previous stage and did not work. This section may be left blank during the definition phase. Timing. The completion of the various sections that comprise the process control narrative shall be in accordance with the project timeline. Many sections have input in more than one phase of the project. During the definition phase, the minimum required input is a complete definition of all functional requirements for the particular control loopets. For example, during the definition phase, the functional requirements for initialization of a loop should be defined, but the details of how this is achieved is not included until the implementation phase. Detailed narratives for logic sequence batch systems. A detailed narrative shall be made for all complex logic loops or systems, all sequence and all batch systems. The sequence control narratives shall describe the normal sequence and also off-normal operation, failures, trips, and recovery. The detailed narrative shall include at least the following information: objective, functional description, operational and implementation aspects, sequence programs, history, timing. These are described in the following sections. Objective. This section shall contain a description of the process reasons and control objectives for the particular logic sequence batch system. Functional description. This section includes the following: places the sequence in a process context, describes the structure of the logic sequence batch scheme, gives an overview description of how it works. All steps in the sequence shall be described in this section. An overview of the logic using sequence function charts, SFC, shall be included to illustrate the logic together with a reference to any detailed drawings. The actions and conditions are detailed in another section as described in sequence programs. The batch sequence shall be structured in accordance with the functionality described below. The process sequence of the recipe and phase is defined as a normal sequence, which exists for each phase of the process. During the running of the normal phase, a number of checks, abnormal checks, are continuously carried out. When one of the check conditions is not fulfilled, an abnormal sequence will be initiated. The abnormal checks are started and stopped at the start and the end of the normal sequence. When the abnormal sequence is activated, it will bring the reactor to a safe condition for that particular phase, and it will indicate to the operator which condition caused the abnormal sequence to be activated. After correction of this condition, the operator can restart or continue the operation. In addition, interlocks are defined for valves, e.g., a valve cannot open when a number of other valves are not closed, and vice versa. The interlocks are always active. They are independent of the running of the recipe sequence. To enable the continuation of the sequence when a failure of a field instrument occurs, ignores have to be built in. For example, consider a situation where the sequence must continue after a feedback signal from a valve, e.g., open position detector, is received. When this position is faulty, the sequence will come to a halt. To enable the operator to continue, an override function ignore has to be built in. All ignores are reset at the start and the end of the recipe sequence. During detailed design, further structuring of the sequence in smaller phases, basic operations, and corresponding abnormal sequences may be required as more details are known. All confirmed valve positions and motor status shall remain confirmed at all consecutive steps until the KS instructs to change the valve position or motor status. If the confirmation of a valve position or motor status is lost, or when a confirmation cannot be obtained on request, the KS shall initiate an action to let the sequence go to a safe position. An alarm shall be generated, and an indication of the confirmation that could not be obtained shall be given. If in the program no action is stated in the case of non-confirmation, the KS shall give an alarm and stop the program. A message indicating in which step the stop occurred and for what reason shall be generated. The operator is to decide how and where to resume the program. The conditions that are required to allow the start of critical operations, as well as the conditions that will initiate a shutdown of these operations, are specifically summarized in the text. Operational and implementation aspects. This section shall detail the implementation details and the operational aspects of the scheme. It shall be completed in the definition phase to the extent that data is available. Final development and implementation details will be completed in the implementation phase. This section shall include all status indications, messages, and alarms required to keep the operator informed about what is happening. Switches, push-button, selector, and timer functions that allow the operator to start, stop, hold, select, manipulate. For sequence control-related timers, the reason for the timer, whether it should be visible to and adjustable by the operator, and the rationale behind the setting. The actual timer setting shall reside in a separate document called the Alarm and Trip Setting List. In addition, this section shall detail what the operator requires for support and troubleshooting, including special graphic display requirements and customized support functions. Sequence programs. The sequence program shall be broken down into logical steps in the form of standard modules, which can be linked to define the total requirements. Each of these steps should be small, independent, and related to a specific process function, e.g., heating, holding, and cooling. The sequence structure shall result in maximum reuse of code and allow sequences to be constructed from subroutines. Where possible, this shall also result in minimum maintenance requirements for software during operation. For each step of the logic, details shall be provided of the actions taken, valves moved, controllers initialized, and termination conditions for every step. This section shall be written in structured English pseudocode. Structured English uses words including open, close, start, stop, enable, disable, reset, if then, else, go to, wait. Commands shall be described using active verbs in expressions like open KBS 105 invent and blanketing line. Tag number and service descriptions shall be used. Checks and conditions shall be described using expressions like confirm KBS 105 in reactor vent and blanketing line is closed. Tag number and service descriptions shall be used. The intention is that this code will be used by the DCS vendor to implement the sequence without ambiguity. A list of all instruments tags with their service descriptions shall be provided at the beginning of the sequence programs section. Sequence function charts, SFC, shall be provided to indicate the logic flow for the sequence being described. Each step will be indicated in the SFC. If a particular step is complex, then a more detailed SFC for that step should be produced. These shall be attached as an appendix to the narrative. For complex sequences, valve equipment timing charts are to be produced to provide an indication of what state valves are in during each step of the sequence. Simple sequences, where there are only a few valves, do not require timing charts. During the implementation phase, all generated final code shall be extensively commented to allow for easy debugging and future modification. It is anticipated that the quantity of comments will be comparable to the amount of code. History. See earlier section on history. Timing. The completion of the various sections that comprise the sequence control narrative shall be in accordance with the project timeline. Many sections have input in more than one phase of the project. During the definition phase, the minimum required input is a complete definition of all functional requirements for the sequence logic control. For example, during the definition phase, the functional requirements for communication between individual sequences should be defined, but the details of how this is achieved is not included until the implementation phase.